the conservation of angular momentum. We know that things that are moving, things that have velocity, have momentum. So things that are rotating have angular momentum. And if there is no torque, no net torque acting on the rotating object, there will be no change in its angular momentum. The angular momentum, we know, is equal to the product of moment of inertia I times angular velocity omega. If that remains a constant, I can change one of those things, let's say increase the angular velocity if I decrease the moment of inertia, because the product of the two must remain a constant. Let's look at some examples where I'm going to change the moment of inertia by changing the mass distribution and see the resulting change in the angular velocity omega. Here I have a turntable, and I'm just going to sit on this turntable and it will allow me to spin around. I've put some weights in my hand. I'm going to push off the floor to get me going, and you see as I pull the mass in towards the axis of rotation, my angular velocity increases. Divers use the same principle to help them spin and to stop spinning when they dive. Here you'll see Greg Louganis as he jumps off the platform. He tucks his body into a ball, and as he enters the water, he untucks to stop his rotation. Here you see it again with some female divers tucking their bodies to spin and then untucking to stop spinning. Here's an interesting example. This is the Mars rover on its way to Mars. Part of the trip required that it start to spin. So here's a torque producing a spin, giving it angular momentum, and then it gets going through space, and then it needs to slow the spin, so it releases out some tethers. Let's see that again. It's spinning, and as the masses fly out, it causes the rotation to slow. The angular velocity decreases as the moment of inertia increases.